Here we'll discuss the substitution rule, which is the first non-basic method of integration that we will study. We'll start with talking about indefinite integrals and then move to definite integrals. So let's consider this, the integral of sine of 4x dx. Well, the integral of sine is negative cosine. So let's see, is this equal to negative cosine 4x plus c? Well, if I try to take the derivative of negative cosine 4x plus c, I get 4 sine 4x, which is not really what I want. I just needed sine of 4x, which tells me that the actual integral of this will be negative 1 over 4 cosine 4x plus c. That way I have this negative 1/4 here to balance out this 4. So these are kind of like we're going to do with substitution. I'm going to have to set up a method to be able to solve these a little more simply than just trying to guess and then check. So we know the chain rule. If we have a composite function f of g of x, where the derivative of big F of x is equal to little f of x, then our derivative is f prime of g of x, g prime of x, which is the same thing as little f of g of x, g prime of x. And this is the idea. We want to undo the chain rule. So for that, we have our substitution rule. So I'm going to let u be equal to g of x, and g of x is some continuous on some interval. We're supposing f is continuous on the corresponding range of g. So on this interval, f of g of x, g prime of x, we're going to change to f of u du. So I'm going to try to set up this function for u equal to g of x and then substitute it in. So my procedure, with my indefinite integral, we need it to contain some kind of composite function, f of g of x. We want to identify the inner function u of g of x such that some constant multiple of g prime of x appears in the integrand. After that, we can substitute u equal to g of x and du equal to g prime of x dx in the integral. Evaluate this new integral with respect to u. And then finally, substitute our expression back in so that our final answer is in terms of x. So for example, for this particular example, I'm going to let u be equal to the inside of the parentheses. 2x squared minus 5. In this case, du would be equal to the derivative. The derivative of 2x squared is 4x. The derivative of negative 5 is 0. So now I have du equal to 4x dx. So this parenthesis will actually become u cubed. And this 4x dx will become du. And this is going to be much easier to integrate. We know that this is 1 over 4 u to the 4th plus c. Substituting back in for u gives me 1 over 4 times 2x squared minus 5 plus c. So before, we may have to just multiply this expression out to try to integrate it, but now with substitution, we can do it much simpler. Let's try this one. In this case, our inner function is going to be the exponent, 7x. So the derivative would just be 7 dx. So the e to the 7x becomes e to the u, and the 7 and the dx becomes du. The integral of e to the u du is just e to the u plus c. Substituting back in, I get e to the 7x plus c. Now let's consider this one. Just like my first example, I'm going to let u be equal to what's inside of the parentheses. X cubed minus 4. That gives me that du will be equal to 3x squared dx. However, you'll notice in this integral, I don't have a 3x squared, I just have an x squared. And this is why it works for any constant multiple of the derivative. I'm going to divide both sides by 3 here to make this 1 over 3 du equal to x squared dx. So now, this x cubed minus 4 to the 9th becomes u to the 9th. The x squared in dx becomes 1/3 du. So this is now 1 over 3 u to the 9th du. When we integrate this, we add 1 to the exponent to get 10 and then divide by that. So this will now become 1 over 30 u to the 10th plus c. Substituting back in, I get that the final answer is 1 over 30 times x cubed minus 4 to the 10th plus c. Let's try this one. It doesn't really look like we have so much of an inside or outside function here, but let's go ahead and keep to the pattern. So before I was setting u equal to what's in parentheses, but another way to think of that is what's being raised to a power. So in this case, I'm going to let u be equal to sine of x. The derivative of sine is cosine, so du will be equal to cosine x dx. So that means this is the integral of u cubed du, which is 1 over 4 u to the 4th plus c. So my final answer, 1 over 4 sine to the 4th x plus c. Let's try this one. This one definitely looks a lot stranger, and it should. So this one's actually going to require a little bit of work. So I'm going to let u be equal to x minus 5. This means that du is just equal to dx. Equal to. So far, I can turn the denominator into the square root of u. The dx just becomes du, but I haven't dealt with this x on the top yet. So if u is equal to x minus 5, I can say that u plus 5 is equal to x. So I'm going to turn the top into a u plus 5. Simplifying this, I get the integral of u to the 1/2 power plus 5 times u to the minus 1/2 du. So adding 1 to the exponent gives me 3 over 2. So I have 2/3 u to the 3 over 2. Adding 1 to the second exponent gives me 1/2. So I get plus 10 u to the 1/2. Plus c. We can then substitute back in. So I have 2/3. U is actually x minus 5 to the 3/2 plus 10 x minus 5 to the 1/2 plus c.